So I'm here again in Stockholm in the middle of August on a strange day weather-wise. We veer from sunshine to clouds on the campus of RISE with a senior scientist for RISE, a lady who is a geochemist and an astrobiologist and also an expert on Mars and part of the Perseverance rover science team. She is actually Sandra Siljestrom. Is that correct, Sandra?
Sandra Siljestrom, yeah.
Yeah. Who is part of the science team. You are a Mars sample shepherd. Tell us what that means.
It means that, so I'm part of the Mars 2020 science team, and as a sample shepherd, I help lead the discussions for collecting the samples on Perseverance and also write the documentation around the samples.
And you actually have input on where this rover on Mars is going to sample.
Yes, that's our job.
And so what do you look for when you're looking for a sample? And as an astrobiologist, you love all geochemistry, you love all geology, I assume, but you, as an astrobiologist, you are looking for microfossils, ancient microfossils on Mars. So what excites you most when you are looking around trying to figure out where you used to sample?
Well, there are certain environments where these type of signatures are accumulated and where life typically, where you typically find life. So you're kind of looking for those type of environments. So those are kind of like lakes and rivers where you see there's interaction with water, where maybe we have some data from space that says there's a particular accumulation of certain minerals that are good for preserving and accumulating biosignatures. So those are also areas we're going to. So all those kind of environment that are good for, where you would find rocks that might contain these biosignatures.
And you told me in our interview just now that there are 4 samples that interest you most.
Yeah, so or you could say it's not 4 samples, it's like 4 different areas.
4 different areas.
Yeah, so one is the latest sample we collected.
Sample 22, is that
yes,
right?
Yeah, which was this kind of fine-grained rock at an area called Bright Angel. We also had a number of different samples collected at a previous region called the Margin, because it's kind of right inside the crater. So we are here in the Jezero crater that was once an old lake, and it's just on the margin of that kind of lake. So those samples contain a lot of these minerals formed by water, carbonates and hydrogen silica, and these are typical minerals where you would find biosignatures on Earth. So we typically think about when we want to find biosignatures, we go and think where we would look on Earth, and then we go to as similar environments on Mars that we can find. There's also a third place which I think is very exciting, which is called the delta front in this lake. It looks like there was an old delta, and if you want to look for organic molecules is what builds all life on Earth. So we're interested in finding those organic molecules. You typically find it in the delta front, so we collected some fine-grained samples there too, and those are also very exciting. So I think those are my 3 favorite places where we collected samples.
But sample 22, the one that got all the media attention about 2 weeks ago, I think it was they actually disclosed, or there was a press release on July 29th. I don't know, when was that sample actually recorded?
In July 21st, actually.
July 21st.
Yes.
And did you watch them do it remotely?
So you don't actually see there are pictures. You can't see it directly. You get the pictures afterwards, right? So the rover does its thing, collects its images, and then sent down. But I saw the picture as they came down, and you could see. So we get a picture of the actual coring, and then we actually get a sample. So actually the core is directly cored into the sample tube. And then you take a picture at the end of the sample tube before it's sealed. So
and this, did you immediately see the leopard spots or
the leopard spots we saw before. So before we sample, we do a very thorough investigation of the area we want to sample. So we had all these images and chemical analysis before we decide to sample. That's how we decide to sample. Like this is really
Because you saw the leopard spots on
the
this,
leopard spots and several other features.
on the sedimentary rock.
Yes.
And the sedimentary rock is simply a rock that
Typically form in sedimentary environments. So a typical sedimentary environment is a lake or a river. So you have like sediments, falling through the water column, sedimenting on the bottom of, for example, a lake, and then you have another layer, and then as the pressure increases because of the layers that's building up, you get a bigger form.
So we've been fooled before. The world has been fooled before with the Allen Hills meteorite, which was a Mars meteorite, and initially announced as potential sign of life on Mars from the morphology of the features in the rock itself. But you don't think that's going to happen again, because we're much further along in the context for where this sample came from.
One important thing with the samples that we are collecting is all the context we're collecting. We know exactly where we drilled this core. We know a lot about the rocks surrounding where the core was cored, but also all the rocks around and the setting, compared to the Martian meteorite, which we hardly know where they came from on Mars, the whole planet basically.
We don't know at all, do we?
No.
We have no context.
Well, there's maybe some clues to maybe it's that kind of area, but not more than that. We know very little.
We can't say with any certainty.
No.
And so that was one of the problems. But
Yeah.
with this sample, the leopard spots are a potential signature of what? Either if it's abiotic, it could be high temperature olivine and
So
pyroxene.
these leopard spots or reduction spots, as they're chemically called, are typically can form in different ways. One way, it's at low temperature, and then microbes typically are involved in this process. But they can also form at higher temperature, and then you don't need microbes. So that's why we call it potential biosignature, and that's why we want to bring these samples back, right? Because we want to investigate, because then we can say, was there a low temperature or was it high temperature? Because you can tell this by very careful mineralogy and chemistry.
And a lower temperature would potentially signify that these spots were caused by biology.
Yeah.
And a higher temperature would simply mean it's an abiotic mechanism to cause the spots.
It would make it less probable that you had biology in. But just saying that it's low temperature is not the final say that it's made by microbes. You would need additional data, which we'd be able to collect. For example, are there organic molecules present in the sample indicating that there were biology? Is there minerals that were formed biology? We might even find the microfossils in there, right? So it's just, but it's a puzzle, right? And all the pieces of the puzzle are needed for building the case for life, right?
But they're called leopard spots because they are discolored and
they look like leopard spots,
like black
right?
spots.
Yeah, so you have this, it's a white core. It's a spot that's white that has like this black rim. So it looks like a leopard spot. So it's more of like how it looks like, right?
Right. And so when we eventually get this back, we will be able to determine this. But you're holding in your hand, when we get the sample back is what I'm trying to say, we will hopefully be able to determine whether or not this is an abiotic signature or actual biosignature of life. And if that happens, if we think it's a biosignature, could we say that this is life, ancient life on Mars, a microfossil?
Yeah, I mean, if we have enough convincing data that says so, then we could say, yeah, there was probably
Pretty definitively.
Life on Mars.
But even on Earth, microfossils are hard to characterize. I mean,
at least very old microfossils are very hard to characterize.
Please hold you're holding what are you holding in your hand?
Yeah, so this is a rock from the Western Australia, Pilbara.
Right.
And you have kind of this dome structures here that you see here, and these are stromatolites. So these are actually it's not the microbes in itself, but the microbes kind of do these microbial mats, but then you have sediments depositing on them, and to continue reach the light you have to put another layer of microbe. So that's why you get this kind of layered structure kind of reaching towards the light. So that's kind of one of the oldest evidence of life on Earth are these type of strata light structure. This particular one is not one of the oldest because it's only 2.5 billion, and the oldest ones are like 3.5.
But this is evidence of life from 2.5 billion years ago,
Yeah.
found in the northwest Pilbara region of Australia. And I assume that you picked this up yourself when you were down there?
Yes, yeah.
Okay. And so this just tells us, I mean, even on Earth, it's not easy.
No, I mean, this is kind of this is kind of the typical things you're looking for. It's not going to be like a big sign saying this is or a green alien saying hi.
Okay. All right. Well, thank you so much for your time today. I thoroughly enjoyed our interview, and thank you for enlightening us on this potentially, very historic sample 22 from Perseverance. Thank you, Sandra.
Thank you.